Welcome to lecture 7, and we will continue with more examples. Okay. So in the last class we saw the example of twisting of a beam. Today we are going to see another very interesting deformation which most of you would have seen it, that is bending of beams. Alright, but I guess in UC class you are not taught what's the formula for the deformation. So if I think of this map again, y equal to y hat of x. So what is this formula for this function y hat? So that is something we haven't, most of us may not have seen it in the UG class or even till now, but we are going to see that today. Okay, that's of course under some assumption. So think of a slab. I hope you guys know what a slab is. For example, a brick, it's a slab. Okay, so I'm just going to draw a picture. So points are A, B, let us see, E, B, and this is of course a short example in the book. It's problem 2.2. And the origin is, let's say, over here, O, and this is the E1 axis having coordinate x1, and that's the E2 axis having coordinate x2, and what comes out of the paper is E3 axis. Okay, so if you want to say, so that's a reference configuration of the slab. Okay, reference configuration of slab. So it's just a planar picture, but you can think that it's also, the slab is extending in the x3 direction, which you can say is like the thickness. Okay, and this thing then becomes, one can say, is the height. Okay, and what comes out of the paper, that's a thickness, or you can say width. Okay, so if I ask you what is the region occupied by the body, so if I denote that by ref, right, ref, so you can write mathematically. So you have to learn to write things mathematically, because that's how people do it in papers. 0 less than equal to x1 less than equal to L. You see what I'm saying is that the x1 coordinate is between 0 to L, isn't it? So suppose that this is the length of the beam. Then for the x2 coordinate, I would say it is minus h less than equal to x2 less than equal to h. Okay, so in the book it is like this, so I guess this height becomes 2h. Then the width, that's minus b by 2 less than equal to x3 less than equal to b by 2. Okay, so that's a reference configuration, and we want to bend it. Okay, so all of you know, when you bend it, when you bend a beam, for example, it bends into a circle, isn't it? So for example, it could occupy the picture that I will just show you. Okay, Let me make it a bit more nicer. Okay, so that's a red one, that's a deformed beam. Now, what's the property of this deformation? So, of course, that means we have to say, we have to assume something. So, one of the assumptions, the first assumption that we will prescribe here is, so let me write down here, assumptions. So it says the displacement of every particle is in x1 x2 plane. Okay, can you see what is this going to, what kind of constraint is this going to impose on y1 hat, y2 hat, and y3 hat? So displacement of every particle is in x1 x2 plane. Anyone? So some of you are saying that it will not depend on x3. So I guess what you mean to say is that y1 hat is just a function of x1 x2, y2 hat is a function of x1 x2, and y3 hat is a function of x1 x2. Is that what you're saying, or you mean for the displacement? See, if you say, for example, this y3 hat is just a function of x1 x2, so what this means is that for every x3, they are all going to collapse onto x3 equal to some constant plane. So what this means is that y3 hat of x1 comma x2 comma let us say 5 will be same as y3 hat of x1 comma x2 comma 6. Does that look fine to you? I don't think so, isn't it? So this is uh, this is ruled out, this particular thing, right? Because if you do that, I hope you can see that along the width of the beam, the entire thing just collapses on a single plane in x1 x2 plane. But that is not something we want. See, what it says is that displacement is in x1 x2 plane. So if you think of u1, for example, u1, so it has, so u1 hat is a function of x1 x2. Okay, so u1 hat is a function of x1 x2, u2 hat is then a function of um, x1 x2. Well, it can actually u1 hat can also depend on x3. All that it says is that the displacements are in x1 x2 plane. It doesn't say that it has the same displacement for different x3. So we can still allow this, and likewise this is also allowed. See, displacement is in x1 x2 plane. That means displacement has got only u1 and u2 coordinate. Okay, so what this means is that displacement has only u1 and u2, no u3. Okay, so this implies u1 hat is the full function, full general function, but u3 hat is then equal to 0. And I guess Meenal is writing here that this also implies that y3 hat is then simply equal to x3, right? Because u3 hat is 0, so y3 hat is x3 plus u3 hat. So y3 hat is equal to x3. Okay, that's the only restriction that we are getting as of now from this assumption. All right. Now let's look at another assumption that the book says. See, this is how, so we are trying to learn how we can find out the formula of deformation given some assumption, physical assumption. So I hope all of you are with me. So the second assumption says every plane x3 equal to constant in this reference region deforms identically. Okay, what do you think? What is this going to lead to? Anyone? What does this mean? So every plane, see x3 equal to constant. So think of different planes. If you cut this slab, in the x1 x2 plane at different x3, you get squares. So those are the planes, and it says all such planes deform identically. What do you think? So if you think of displacement, for example, u1 hat, which is a function of all three as of now. So it says every plane deforms identically. It's the same displacement. So somebody has already said, Mir Rashid, that no variation along B, right? So, and B is in the E3 direction. So that means this U1 hat is not a function of X3. Very good. So Bipul also says U1 and U2 are independent of X3. So this implies U1 hat is just a function of X1, X2. Likewise, U2 hat is also just a function of X1, X2. Okay, I hope this makes sense to everyone. Okay, all right. So let's go to the third assumption. So you see, what this tells us is that you can restrict your analysis to just one of those planes because each of the plane is deforming in the same way. So you can restrict the analysis in just one of those planes. I hope all of you are with me. Okay, then the third assumption is a very, it's a bit difficult assumption, but some of you can, of course, figure out. So it says that each straight line x1 equal to constant is carried into a straight line in the deformed configuration. Okay, Furthermore, each of those deformed lines for different x1 pass through the same point y1 comma y2 is equal to some 0 comma gamma l. So let us try to see what does this tell us. So first of all, each of the lines here corresponding to x1 equal to constant, okay, they it's carried into a straight line. So for example, identify a line which is x1 equal to constant. Isn't this that line? That's x1 equal to constant. So this material line has x1 equal to constant for all the points. And it says this line has to be carried into a straight line only. It can't become curved. So can you see what does this mean? So that means after deformation, this line is going to be something like this. Okay? And when you extend this line, so you will have all such vertical lines converting into straight line only. And it also says all those lines when extended, they all pass through the same point, which is 0 comma gamma l. Okay, it does not say anything about whether the length of the line is changing or not. Can you see what does this physically imply? First of all, the line remaining straight. What does this physically imply? So somebody is saying transverse shear strain is 0. Normal to the plane will be normal. Circular curvature. All meet at one point. Yes, they all meet at one point, that is 0 comma gamma L. Linear strain distribution. So I think let's not get there. Just think simply what is happening to the body when the line remains line. If you think of this cross section, take a cross section. So if I make this picture 3D, um, so I hope you can see the 3D picture. And then think of a cross section of the beam. So the cross section is, for example, defined by cross section plane is x1 equal to constant. That's the cross section plane. So what's going to happen to that? See, the first assumption says, sorry, the second assumption says every plane x3 equal to constant deforms identically. And then the third one says each of the line x1 equal to constant bends into a straight line. So doesn't it say that cross section remains planar? So the cross section remains planar. That is it. It doesn't say whether the um, does it remain the same or not. All that it says is that cross section, a plane section remains plane. So you must have heard of this hypothesis. So what this says is that plane section remains plane. Okay, that's from the first one. Second one says each of those deforms line for different x1 pass through the same point 0 comma gamma l. Okay, so we'll get back to this point a bit later, but let's proceed for the next assumption. So the next one says each straight line x2 equal to constant is carried into a circular arc centered at 0 comma gamma l. Okay, so x2 equal to constant. What is that line x2 equal to constant? So can you identify one such line x2 equal to constant? So this is that line. Isn't it? X2 equal to constant. And it says that gets carried into a circular arc which is centered at 0 comma gamma l. So this one goes to become like this. Sorry, I have to use red one. So it deforms into a circle. So with this, can we figure out what will be the formula for the deformation? See, what we see is that it is bending into a circle. So can we, for example, say that see y3 is equal to x3, that is already known to us. Now we have to bother about y1 and y2, isn't it? So can we say that y1 is equal to um, let us say some radius which is a function of x1 x2. See, we are trying to use cylindrical coordinate because it's getting deformed circle, right? Times sine theta of x1 x2 and y2 is then this point gamma l minus r of x1 x2 times cos theta of x1 x2. See, because it is bending into a circle, right? So that's kind of makes sense. So somebody says bending into circle is an assumption, or in practical also it bends into a circle. So that's a very good question. So in fact, if you have pure bending of beams, then it indeed bends into a perfect circle. So it's what is called a universal solution. If you have pure bending of beams, that means you don't apply transverse force, but you are just applying bending moment to it, then it bends into a perfect circle. Okay. Okay, now what can we say about these functions small r and theta? Can we say something about those functions? For example, will theta depend on both x1 and x2? So see, what is theta then? Theta is like, this angle, that's theta. So any point which is here, which was originally having x1, x2. So for this point, you have to know what is theta of x1, x2, and what is this radius. So this distance, small r, bending into a circle, no? So there must be a radius and a theta for each point x1, x2. And that's what we just wrote down. So once we know r and theta, then the deformed coordinates can be easily found out. See, so here is the origin. So this is your y2. This is your y2. And that's your y1. Okay, and you can see that y1 is indeed radius times sine theta, and y2 is that full radius, or gamma L, I should say gamma L, because that's where that point is, no, the center of the circle, gamma L minus radius times cos theta. Okay. Anyway, so now what can you say about this radius and theta? So somebody is saying pure bending we have already studied, and that looks real simple. Why we are making it little complex? Okay, so when you did pure bending, did you find out this formula y1, y2, and y3? I don't think you found the formulas. You simply, you know, said that take a point at some distance y from the neutral axis, and then because it's bending into a circle. So you did all such things, but you never found this formula. Here we are trying to find out this formula, okay, y1, y2, y3. And even if it is, if it is easy, let's find out the formula, and you see that it is not easy. Finding the formula is not easy. That's why it is looking complex to you, right? So problem which you have already solved, the objective may have been something else, and that's why it was easy. But now the objective is something else. So for different objectives, the level of difficulty can change, right? For the same problem, for the same physical deformation. Anyway, so you tell me, if you think that it is easy, what can you say about this function r and theta? So it is indeed the case of pure bending where we say that plane section remains plane, and each of the longitudinal fibers bend into an arc of a circle. That is indeed the case here. So can you now tell me with this representation what will be radius and theta function? Will it depend on both x1 and x2? Likewise, theta, will it depend on both x1 and x2? What do you think? For example, think of the theta. Should it depend on both x1 and x2, this theta? So what you see here is that, think of all these points. Shouldn't they all have same theta? Because it's on that straight line, no? They all have to have same theta. But what is the difference between those points? They all have different x2 coordinate. They all have different x2 coordinate. So that means the theta should only depend on x1. Okay? So that's what I can say from here, that theta just depends on x1. Okay? So Rahman says it will depend on both x1 and x2, but you see, you are not correct. Just like I said, those points, they all are on the same straight line and they all subtend the same angle theta from the geometry. Okay? If it depends on theta, then that will not remain a straight line, it will become curved. Okay, if theta depends on x2 also, then it will no more remain a straight line. What can you now say about the radius r? As per our current assumption, what do you think? This radius r, should it depend on both x1 and x2? So what you see here is that each of these points, they have the same radius, isn't it? Because it has to bend into an arc of a circle. So they have the same radius. But what is varying on those points? For those points, what is varying? x1. So x1 is varying here. So what we figure out is that the radius should not depend on x1, right? So radius, therefore, it should only be a function of x2. So many of you are saying this. So from here, we can say that radius is just a function of x2. Okay, so this is all that we have found out. So y1 is equal to some radius which is a function of x2 times, let's see, sine times theta of x1, and y2 is equal to gamma L minus again the same radius as a function of x2 times cos into theta of x1. All right, can you further, let's make the problem a bit more difficult. I mean, let's ask more difficult question. Can we say something about the function of radius, I mean dependence of radius on x2? Can we say something about that? Or dependence of theta on x1? Can we say something about that? Anybody? As per the given assumption, or let us say some of you have already seen pure bending. So what do you think? What should radius be function of? What should theta be function of? So Deepshikha says directly proportional. Which one directly proportional? Okay, so Shubham says R is linear in x2. So maybe something like R of x2 is equal to, say, some R naught, and minus x2. Can we say that? See, this is what you had when you did it in the undergraduate class. You said that r of x2 is simply some radius r0 minus x2. You remember that as you go above the neutral plane by x2, then the radius is also just decreasing by the same amount, isn't it? So there is a neutral plane here, and I'm not going to get into that. But as you go above by x2, the other plane that you see, for it the radius is simply r0 minus x2. But you see, that was just an assumption. Why would you say that there is no change? That assumption implies that the height, for example 2h, does not change when the beam bends. When you say that r is equal to r0 minus h2, sorry x2, then the height is still 2h. But why should that be, you know, why should we have that assumption? For now, our assumption does not say that what should the radial function look like. And in fact, for a general deformation, in case of pure bending, that is not true also. Okay, so for a general, for a finite bending, this is just an assumption. So this is actually an extra assumption which is not there in any of those four assumptions that I have listed here. So it's an extra assumption to simplify the problem. It's an extra assumption to simplify the problem. But now, because you guys are master's student or PhD students, you should see that this is an assumption. It is not a reality. Okay. Similarly, what do you think of this theta x1? How should this look like? Theta of x1? Okay, Subham says theta of x1 is equal to x1 divided by r naught minus x2. What do you think? Does it look fine? But you see, this representation that you are just highlighting, okay, you are now saying it's only on r naught, because now both x1 and x2 are there, no? So that is certainly not true. But then you say x1 divided by r naught. How many of you agree with this? So again, that must be based on this assumption over here, because that only gives you the concept of r naught. In our assumption, there was no r naught. So yeah, that is what one does when you do pure bending. You say that theta is, this is what it is, because what is happening is we are tacitly assuming that x2 equal to 0 plane is the neutral plane here. Okay, and so for example, if this were on the neutral plane, so the curved length is same as the original length. So the original length will be x1 because this point was at x1, but the curved length is now r naught into theta. So therefore, this theta is x1 by r naught. Okay, but that's again an assumption. It holds when you have uniform bending. In case you don't have uniform bending, then theta prime, see from here, from this thing, what you see is that theta prime is equal to 1 by r naught, a constant. But in our deformation picture, based on this four assumptions, we are nowhere saying that theta prime has to be a constant. Okay? But when you do pure bending, it does turn out that theta prime is a constant. Okay? And then you can say that theta is linear in x1 and given by this formula. Okay, Meenal says, but if every x2 equal to constant line is bending circularly with the same center, then they should be like concentric arcs, and then h should remain the same. H. What is h here? Oh, you mean the height. See, it can bend, it is indeed bending into concentric arc, but the distance between the concentric arcs can change, right? There can be compression or extension along the x2 direction in the beam, and therefore h need not remain the same. Is it okay, Minal? See, what I'm saying is that in this picture, when the beam is bending, this distance need not remain 2h, because it may very well expand or compress, right? Because you see, you're not applying anything on the, so it's a free expansion in those directions. So you're not constraining it to remain 2h. Since it's a free expansion, so it can change. And when you do finite bending of beams, you will indeed see that it is changing. But when we do linear elasticity for undergraduate course, then the best approximation is that h remains constant. That's a very good approximation to work with. Okay, so you see, you guys have already done bending, but you saw, I think, some extra insight. Okay, so that's about bending of beams. Another deformation. I would like to, do some more example. Um, so you see, in all these, the two twisting, torsion, or bending, we got the formula for y, right? This is the formula for y, and from here you can also find out the deformation gradient, isn't it? Fij, and you will indeed see when you find it. For example, Fij is del yi over del xj. So when you find it, you will indeed see that these components depend on x1, x2, x3 also, isn't it? So you can see that deformation gradient indeed changes from point to point. Okay, as in this example. But there are, several interesting deformations where deformation gradient does not change from point to point, and they are called uniform deformation case. So we have another class of deformation that is called uniform deformation, in which deformation gradient is a constant. That means it does not change from point to point. Okay. Now, do you recall that we had derived that dy is equal to big F is a function of x, dx. I hope you can recall this. The deformed line elements and the undeformed line elements, that's how they are related. But if f is constant, so for the case of uniform deformation, it is simply sum f into dx, right? Then you can see that we can integrate this, isn't it? And what you get from here is that y is equal to f of x, f into x, okay, for a constant f, plus the constant of integration, right? So, let us, for example, write this as f naught so that we know that, okay, it is a constant. So we can also say here f naught. And we can drop this c just for, you know, without losing actually any generality, we can drop this c. Can you see what will this constant c do? The c is like doing pure translation to the body. So whatever you get from y equal to f naught x, you're further adding to it a constant c to every point. So it's like displacing the entire body by the c, rigid translation of the entire body by c. So we can, as far as analyzing the deformation is concerned, we can neglect the rigid translation. Okay, so without loss of generality, let's say that c is equal to 0. I can write here it corresponds to rigid translation. Okay, so that means in case of uniform deformation, you can say that y is equal to f naught into x. And there are some really interesting uniform deformations that we are going to see now. Okay, any questions so far? So think of a deformation that is the following. So say f naught as a tensor is given by this formula, lambda 1 e1 tensor product e1 plus lambda 2 e2 tensor product e2 plus lambda 3 e3 tensor product e3. Okay, for lambda 1, lambda 2, lambda 3, some constants. So if you write this in matrix form, so this is a tensor form, but using this, when you write it in the matrix form, so y will have the three components y1, y2, y3, and f naught will yield a matrix multiplied by the column of x, which is x1, x2, x3. Okay, and what can you say about f naught? What will f naught look like? Given this tensor form of f naught, what will the matrix form look like? Any idea? Identity, diagonal matrix. Yes, so it's going to look like a diagonal matrix. Because you see each of these, for example, when you start writing in the matrix form, the first one is simply lambda 1 into e1, which is 1 0 0 times 1. The second one has to be transposed, right? You remember 1 0 0. So this is equivalent to lambda 1 0 0 0 0 0 0 0 0. So the first one gives you a matrix with lambda 1 at 1 1. The second one will give you a matrix with lambda 2 at 2 2. And the third one gives you a matrix with lambda 3 at 3 3. So what you have here is lambda 1, lambda 2, lambda 3, 0 0 0 0 0 0. Okay. And now you can work out the multiplication. Then you see that y1 is equal to lambda 1 x1, y2 is equal to lambda 2 x2, and y3 is equal to lambda 3 x3, isn't it? If I want to draw this pictorially, so you can think of, let us say, a coordinate system, and then you have a cuboid, suppose. Okay, so suppose you have a cuboid here, and let us say this is E1, that's your E2, and this is your E3. So you can see that according to this map, the length, if, or let us say this is cube, each of them being 1 1 1. Okay, just to simplify. So after deformation, how will the cube look like? It's going to become a cuboid, isn't it? Maybe something like this. Sorry, there is some space constraint here, so maybe I do this. And what will be this length? This is lambda 1. What will be this one? This will be lambda 3, and this is then lambda 2, isn't it? So this is a case of what we say triaxial, extension. So you are applying deformation in all the three directions. So cube becoming a cuboid. What if you set lambda 3 equal to 0, for example? Sorry, 1. If you set lambda 3 equal to 1, then what is this going to look like? So that means, in the third direction, there is no change in length. So it's like a planar deformation. There's no, it's a plane strain problem. So this leads to plane strain problem. Special case of plane strain problem. Okay, so I think you guys have a class. So I'll take it from here in the next class. All right. So see you all in the next class. That is on Friday. But I'm still here. If you have any question, you can ask me. Say again.
Okay. So in the bending case, you have written theta, then you have written theta prime. So
So theta prime is, if theta is a function of x1. So theta prime is the derivative of theta with respect to x1. Okay, so prime means the derivative with respect to argument.